Hello and welcome to another video. In this video we're going to be doing binary tree right side view. And in this problem it's pretty straightforward. You're given the root of a binary tree and you need to imagine yourself standing on the right side of it. Return the values of the nodes you can see ordered from top to bottom. So essentially what you need to be doing is you need to be returning nodes for every single level. Like the rightmost node for every single level is basically how that question is broken down. So for this tree you would return these three nodes, and then if you had something like the second example is 1, null, 3, you would return 1 and 3 and so on. And so if you did have some big tree, you know, like 2, 4, then maybe this has like 6, 8, something like this, you would just literally return the rightmost node at every single level. So you return this 1, 3, 6, and 8 would be your answer. And so let's get an intuition of how we could do this, right? So one simple way we could do this was we could just do like a breadth first search, and we could take an array at every single level, right? And so we'd have like 1, and then we'd have 2, 3, and so on. And then we can just take all those arrays and just take the rightmost value in each of those. So that is like one valid approach. But is there a way we could do this without actually making like an array of outputs? And it turns out there is. So all you have to do is if you just have a function that keeps track of the level you're in, and we can just make sure that the order we iterate through this tree is going to make it so we always visit the rightmost value last. And that's pretty straightforward to do, right? So we can just literally say like, okay, let's just iterate, like we'll start at the root, and then let's just go left and then go right. And that way the rightmost value always gets visited last, and then we can just say like, okay, if we have a value in here, I'll just replace it by whatever we have. So let's see what that's going to look like, right? So let's just do, so we're going to have some output, and then we can just say like, let's say the root is level 0. We can just say, if we visit something and our result isn't long enough, let's just add like length to make it long enough. So for this example, you would say like, okay, our result is length 0. So we need to add length, so let's just add some length, and then let's just store that variable there. So we're going to store 1 here, and then we're going to go left, and then we're going to go right. So that's going to be, so here, we're going to check this value, and we're going to say, okay, this is at level 1. Is our result long enough? No, it's not. So we're going to need to add something here, and then let's just store that in there. And so we are going to store the 2 now. And then we're going to go left again, and we're going to say, is our result long enough? No, it's not. So let's add something there, and we're going to store the 4. And now we're going to recurse back here, and we're going to go right over here. So in this one, what level is this? This is level 2. And now we just say, oh yeah, there is something in level 2. So let's just replace what we had with what we have now. Because the way we're doing it is we are going to actually visit the rightmost node last. So we're going to put in the 6. We're going to visit this 8. This is level 3. Is there something at level 3? No, there isn't. So we're just going to put the 8 in. So I guess technically you don't even need to like add something to the result. You just need to see is there something there? And if there's something there, replace it. Otherwise, you're just going to be appending. Because you're guaranteed to be, if you're at a new level, you're guaranteed to be at like one level deeper than the current length of the result, right? Because if you're at level 3, you had to have come from level 2 and so on. Okay, so now we're going to come back to the 6. Then we're going to come back to this 2. And now we're going to visit the 3, and that's at level 1. So we're going to see, is there something at level 1? Yes, there is. So we're going to replace that with a 3. And now if you actually look, we have 1, 3, 6, 8, which are the rightmost nodes. So we have this node. Sorry, it's a little messy, but this node, this node, this node, and this node, and that is our answer. So let's write down our steps. For 1, have a result array. Then have a function with a level. We have a few cases. If the level is deeper, if the level isn't in the result, let's append the value, right? Because we're guaranteed to be in like the next one. If it is, let's replace the value. And then we just simply recurse left and recurse right, and this is going to guarantee give us the order that we want, so we visit the rightmost node last. Okay, so now we have enough to code up this problem. Hopefully explain it pretty well. I think it's reasonably straightforward, but it's still good to know. So let's do that. So we're going to have a result. We're just going to make an empty array. Then we're going to have a helper function, so we can call that like traverse. and it's going to take a node and a level, and it's going to say, so there's one, or this is def. So obviously there's the base case of if we don't have a node, so if not node, I just return right away, right? Now, if the level is greater than the result of the result, we can just append it. So we can say like if level is, let's think. So if we're on level 0, length is going to be 0. I think it's going to be like if level is greater than res or length res minus 1, because this would be the last value, then we can just append that value. So we could say res.append node.val. Otherwise, we just need to replace it. So then it's going to be res at index level is going to be node.val. Okay, we replace, and now we go left, and then we go right. So we're going to go traverse node.left. We're going to add a level here, and then traverse node.right, and we're going to add a level there. Okay, and then finally we don't need to return anything. Do we need to return something? No, I don't think so. Okay, so we have all our cases here, and now we just need to call traverse at the root with level 0, and then finally we need to return the result. So let's see what that gives us. Okay, so you can see it's pretty efficient. I don't know if you can make it more efficient. I don't think so, because yeah, I mean this depends on the test, but I don't think you can make it more efficient because essentially we're not using any space other than the result here, and we're just doing a traversal. So let's actually go through this. So technically you aren't saving space compared to a BFS. Like if you get asked this on an interview, like what's the worst case space? So the actually worst case space here is that your tree looks like this, right? As always, you're not guaranteed to have a balanced tree. So if your tree actually looks like this, then you're gonna have O of n space. But let's just go through that when we do the space. So for the time, we are doing a traversal, and we're traversing every single node. So that's gonna be O of n, right? So that's just O of n for like how many nodes are in the tree. We're traversing every single node. I don't know if you can. Yeah, you can't just like cut off nodes. So you might think like, oh, you know what? If I have a tree like this, and I have a node here, I can just say like, well, why don't I just go to the right node only? Well, you can't really do that because you can have a tree like this, right? Where your rightmost nodes are actually this node, but then it's these two. So you can't just go to the right node only. You actually do have to check the left because there might be stuff further down. So you can't save anything there. Yeah, so for the space, so you could talk about like worst case scenario, your tree does look like this, in which case your recursive stack would actually be O of n. But in a average scenario, your recursive function would be log n here, right, for the recursion. And then because we're not doing like a BFS, we're not storing every single value. So for a BFS, it would always be O of n, but for us, it's going to be log n average and then worst case. So you could talk about that in an interview. You know, like assuming you have a semi-balanced tree, it would be a log n, but worst case, it would still be O of n. Yeah, and then you're not counting the result because you usually don't count the result in time and complexity. But if they ask you, you can also talk about that, right? So the result will be worst case O of n as well, because if your tree looks like this, then you will store every single node, right? If every level has one node, then you would store every single node in your result. So if you get asked that, you can talk about that as well. Yeah, but that's going to be it for this problem. Hopefully you enjoyed it. It's definitely a good one to know, and it's a reasonably popular interview problem, so I wanted to go over it. And hopefully you liked the video, and if you did, please like the video and subscribe to the channel, and I will see you in the next one. Thanks for watching.